Welcome to our video about our new directional radiation detector. First, we'll demonstrate this device and then we'll explain how it works. Then we'll explain why a directional radiation detector is useful. And finally, we'll tell you what you can do to get this technology into the hands of people who need it. So let's get started. The direction of the radiation source is indicated by the yellow plume there. No matter where I turn the detector, the plume always points to my radiation source. And we also hear the difference in tone as we turn away and toward the source. So let's turn off the beeps for a while. The detector consists of two CT007M microarmeters. These are highly sensitive gamma radiation detectors. One CT007 will shield the other one. One is in front of the other. Each one has about 3 centimeters of cesium iodide as a detector, and that in itself provides significant shielding. Both detectors then send the data to the phone, and the phone compares the readings that each detector gets, and from there it can tell which detector is in front of the other, and it can get a reading. The result of that comparison between the two detector readings is plotted as a function of the compass direction on the phone screen. This actually works with any of our CT007 detectors. So for example, we could use the CT007F, or we could use two CT007F detectors instead. They're not as sensitive as the CT007Ms, so we would need a stronger source to demonstrate this, or we'd have to turn around more slowly. The CT007Fs are also not as massive, so their mass by themselves wouldn't be enough shielding to for one detector to shield the other, so we'd have to put extra shielding in between. And the way we would do that would be one detector would be held in one hand in front of the person's body, and you would put the other detector in, slip it in your shirt on your back, and again your body would be providing the shielding. You would turn around slowly to find the direction of radiation. The phone still compares the reading in the front detector with the reading in the back detector and plots the direction of the source. Let's get back to our demonstration. So far we've been in the directional mode. Here the beeps get faster as we turn the detector toward the source. We can also go into our dose mode. And in this mode, the counts from both detectors are summed, and you end up with a super sensitive detector. Each individual CT007M gets around 33,000 counts per minute per microsieverts an hour, which is almost twice what a standard microammeter based on a 1-inch sodium iodide crystal gets. Combining the two detectors, we get around 60,000 CPM per microsievert per hour. It depends a little bit on the orientation that we're holding this. And that's about 3.5 times more sensitive than a standard microammeter. And the entire rig is still lighter and more ergonomic than the standard micrometer based on a 1-inch sodium iodide crystal. If you are in a noisy environment, you can always play the tones through headphones, Bluetooth headphones. So one, you're not bugging people around you, and you can still hear the tones. Some people ask, why would I need a directional detector at all? Can't I just run around and take readings? These will increase as I get closer to the source. I can speak from experience that it's not that simple. Say, for example, you're here, you take a reading and you get 1 microsievert an hour, and you go over here, take another reading, and you get 100 microsievert an hour. Now, you would conclude that the reading here is 100 times higher than the reading here, therefore you're 10 times closer to the source here than over there. That means you must be very, very close to the source here. Wrong. In reality, your source is here, and you just have some shielding between the two. And that's the reason your reading over there is lower. This is actually a very likely scenario. You might not have obvious shielding, but a lot of the sources that get trucked around are collimated, like a density gauge or something like that. They're usually collimated and they emit a beam of radiation rather than an isotropic field. So as you walk in and out of the beam of radiation, you would conclude that you're getting closer and farther away from the source. All this time, you're picking up unnecessary radiation dose and you're not getting any smarter. A directional radiation detector will point you in the direction of the source, whether you measure it here or there. And with that information, you can triangulate the precise source location without putzing around and getting dosed up. Then you might say, I can get the direction of the source just by holding a single radiation detector in front of my body and slowly turning around. Where the reading is highest, that's the direction of my source. That does work sometimes. Let's say you take a reading pointing in that direction and you get 1 microsievert an hour, and you turn around and you get a reading in that direction of 1.1 microsievert an hour. So you would conclude that the direction is located in, you would conclude that the source is located in that direction. Again, that's wrong. In reality, the source had some shielding and maybe it moved a little bit. The source or the shielding moved a little bit as you were turning around. And that's the reason you got two different readings here, not because the source is actually located in that direction. Or the shielding between you and the primary source didn't move at all, but there was a secondary source that came close to you as you were turning around. That could have been a really small and trivial source, like somebody carrying a pack of TIG welding electrodes, for example. With our system, you always compare the radiation seen by the two detectors at the same time. So you eliminate any effect of a time-dependent radiation field. Another problem with using general-purpose survey meters in this way is that these are likely not able to detect any difference between a 1 microsievert an hour field and a 1.1 microsievert an hour field. They just aren't sensitive enough, and the reading is going to bounce around too much. Our system is 1,000 times more sensitive than your standard Geiger-Miller tube-based survey meter. To summarize, the CT007M by itself is a highly sensitive radiation detector which will be used to detect and intercept hidden radioactive material. Put two of them together and you end up with the best directional radiation detector available. There are other instruments in the CT007 product line, for example the CT007F, which is optimized for detecting and preventing the spread of radioactive contamination. So, how can you help to get this technology into the hands of people who actually need it? This new technology has been pre-approved under the Build in Canada Innovation Program, or BCIP. We are currently looking for a federal partner. That means that any Canadian federal government can get this technology at no cost to them. So we are interested in hearing from any department that has a mandate for protecting people from radiation exposure, from lost sources, smuggled radioactive material, or nuclear accidents. This could be the RCMP, could be Border Services, it could be the Canadian Nuclear Safety Commission, it could be Health Canada, it could be Emergency Response Canada, or it could be the military. Again, these departments can get this technology absolutely free. It does involve some paperwork between the test department and Public Works, and some time in actually trying out and evaluating the equipment. This isn't a temporary test or a loan. The department gets to keep the equipment. So, if you know somebody who works for these departments, please get this information to them. If you work for one of these departments, please move the information up the food chain to someone who can sign an agreement with Public Works. If you don't know anyone in those departments, please like this video. That will make it show up in YouTube searches and will help spread the information about this new technology. This could save lives if it detects a dirty bomb, and it certainly will save a dose by finding lost sources faster and preventing the spread of radioactive contamination. If you want more information about the Build in Canada Innovation Program, you can Google it. If you want more information about this technology, please follow the link below this video. There is contact information at the bottom of the page. Thanks for watching, and please help spread the word.